There's 101. Correct, though?
Yes, sir.
Recording is on.
Okay. And then we've got, we'll talk about anything in the education or member project show and tell. We've got nothing logged into that, but I can ask the question if anybody's got anything they're working on. And then we've got the roundtable about kit building practices and stuff. And then we've got an update on the DCR. I think what we'll do is we'll do the DCR first, and then we'll do the roundtable last, because that might take a while. Hey, Dave. So, Peter, go ahead.
Okay, well, it's too bad Klaus is not here. But anyway, a couple of months ago, I brought in a book, the Basic Radio book. And along those lines, I picked up quite some time ago from the ARRL, the Basic Electronics book. And this is probably the first one should get for the basic library, to go along with our theme this year of basic, getting back to basics. And what I like about this book is it doesn't get into great detail. So when you're just starting out and you want to learn about different circuits and whatnot, you can pick this up and you'll get the gist, and you won't get yourself bogged down in detail, so to speak. For example, mixers. It's a very short little, you can see, short little topic right up on mixers, but it gets to the basics. It tells you what it does. Input 2 frequencies, and you get out, add, subtract, that kind of thing, and away you go. So the whole book is like that, give or take. See if I can find the index here. I think I could find an index, couldn't I? Anyway, it covers off all the basic circuits. And I think it's a good start to get going on these things. It goes from parallel circuits, voltage laws, a little bit of on math, amplifiers, inductance, impedance. It covers all the usual kinds of things, and but in a basic way. So I don't refer to it very, very often. Once in a blue moon, when I get into a big argument with Dave and I have to start all over again, I'll start with this book, and then I'll progress to this book, and then I'll progress to this book. But getting started, I think this is a good one for the library, starting out to get to the basics, and then you're going to be very quickly moving on to some of the other books, which we can talk about going down the road. But for starting out, I think that's a good addition for your library.
Okay.
Yeah.
No, go ahead. Go ahead. You got more to say?
No, that's pretty much it. Pretty basic.
Okay. I hope Klaus comes in.
Yeah, I just find that sometimes when you can get bogged down in details, and sometimes it's kind of nice just to go back and just start at the basics, read it, and then progress again.
Okay. Is that Cherry? I can't tell. Is that you, Cherry?
Yeah, that's me. That's me.
Oh, okay. Because you're front lit and it's hard to see your face.
Okay. And I'm also looking a little bit different. That's right.
Well, okay. Okay. When you is it possible to set up a profile name while we're on here, or does he have to exit?
No, you can do that. No, you can make out the profile as you're going.
Okay, Jerry, there's a profile there where you can put your name and your call sign if you want.
Yeah, I was trying to see that, where I can put it. I cannot find it. I'm for the first time on Jitsi, so I will figure out where I can put a name. Go ahead.
Okay. All right, next.
Click the three dots in the bottom right-hand corner, and that opens up settings. And the very top one, you click that, and that's where you could put your name in.
Sort of like what you could do, right, Dave?
Yeah, mine. Oh, my profile isn't there. Oh, geez. Here, I'll change it.
Okay. Thanks. I just did mine.
Okay. And Cherry, also too, keep your mic muted until you want to speak, and then in the lower left corner there's a hand there. If you want to speak, that raises your hand, and it gives me an indication that you want to talk. Okay.
Yeah, cool. I'm doing.
Okay. Just mute your mic for now. Okay. Next in line here is Michael with his filter talk. You want to take over, Michael?
Yeah, okay. Yes, I will. Yes, okay. Let me just share now. Can you hear me okay?
Yep.
Okay.
Your screen appears frozen, though.
Can everybody see that?
Yep.
Okay. So, this is a presentation that I did 2012 to the Mississauga Club, and I've updated it since. A lot of the material in the presentation has come, you'll see a lot of it, almost all of it's come from the ARL handbook. I have the 2010 version and also the EMR experimental methods book as well. So that's where I got my stuff. It doesn't mean I know anything. So to start with, what do we do with filters? Well, we use them for power, for example, in power supplies to remove ripple, and in receivers for selectivity purposes, for selecting some signals or rejecting others, and for transmitters to make sure you're not transmitting harmonics and removing undesired signals from your transmission, and other things as well. So let's see. So in terms of power supplies, for example, the top circuit here is just a half-wave rectifier. You just get the half-wave output here and nothing underneath on the negative side. When you put a capacitor across the load here, what it does is it allows the signal, it stops it from dropping all the way down to the bottom. So the signal you get is actually this curve here. And the more filtering you put, the better it is. And if you use a full wave rectifier, it's even better, and so on. So that's power supply filters anyway. In receivers, you got a bandpass filters in the front. You've got IF filters in the IF chain here. That would be crystal filters usually, and you've got audio filters perhaps for your audio output, equalizers and the like. In terms of transmitters, likewise, you've got you filter your microphone audio perhaps. After the mixer, you've got an IF filter here, and this is the post mixer filter, another filter here, and perhaps a bandpass filter or low pass filter on the output to prevent you from transmitting harmonics into your antenna. So these are some of the types of filters out there. There's the lumped and capacitors ones, which is the ones I'm most familiar with. There's crystal filters. I know a little bit about them. There's active filters, which as far as I can see appear to be mostly audio filters. For audio frequencies using op amps, it looks like most op amps don't operate at RF frequencies. There's helical resonators, which are used in repeaters, and then there's transmission line filters, which are used by laying out strip lines on PC board material. So just a bit about terminology. So there's low pass filters, which pass filters only below a certain cutoff frequency. High pass filters, which do the opposite, don't pass only frequencies above a certain specified frequencies. There's band pass, which are a range of frequencies, upper and lower. And there's a band stop type, which rejects only over a specific frequency range. The other thing that's of interest is the order of the filter. It's order. It's the number of inductors and capacitors in a particular filter. And there's another term called group delay, which I don't know very much about. It's just time delay going through the filter.
And those enchanted scars.
Another important thing is the cutoff frequency, which is the frequency at which the filter output of power is halved, and that's the 3 dB point, which is calculated as 10 times the log of the power ratio. And if the power ratio is a half, so it's 50%, then you get 10 log of a half, which is minus 3.03 dB. So that's the 3 dB point, and that shows up on the graph as the point where the transmission losses is 3 dB down the peak. So here's some filter responses. This is the low pass filter here. You can see the 3 dB point is right where the mouse is. Here's another one, a band pass filter, 3 dB points on both sides. High pass filter here, same deal, and a band stop filter here as well, just as examples. There's another factor. It's called the sharpness of the filter. It has to do with, I guess, the Q of the filter, and it's based on the order, which is the number of elements. The more elements you put in, the sharper it is. And this is for a low pass filter. Here's the 3 dB point right here. And you can see, depending on the order, you get a bit more at the top, so less loss on above the 3 dB point and varying degrees of loss below it. So there's the order 3 right there, for example. There's various different filter families. One's called a Butterworth filter, which has no ripple in the passband. That's its characteristic. The Chebyshev filter has ripple, but it's got a steeper, so you pay a price for this particular filter. You get steeper roll-off outside the passband, but you got to deal with a little bit of ripple in the passband itself. And the Cower filter is a different type of filter again, and there's all kinds of others. So here's an example of the Butterworth response versus the Chebyshev response, and here you can see the ripple on the Chebyshev, and there's no ripple in the bandpass, but you can see how much sharper the Chebyshev is compared to the Butterworth filter. And when you design the Chebyshev filter, one of the things you put in is the ripple amount. So just some ideas about low-pass filters. They let frequencies below a particular frequency through, and the way it works is as the frequency goes up, the inductor in the top example, the inductor impedance goes up, so the output to the load drops. And likewise in the capacitor version, as the frequency goes up, the reactance of the capacitor, being inversely proportional to the capacitance, to the frequency rather, goes down. So that way, that's how it works at the higher frequencies. There's less output. And the high-pass filter is the exact opposite. As the frequency goes down, the impedance of the capacitor increases, or alternatively, the impedance of the inductor decreases. So as the frequency goes down, as it goes up, the load decreases. Yeah, as the frequency decreases, the load decreases as well. So lower frequency, less passes through the filter. So just a bit about the design techniques. Basically, you pick your bandwidth, you pick the center frequency, you pick the type of the filter you want to use, and then you got some choices. You can use, do a manual design of the filter, which I'm going to talk a little bit about. So basically, you use normalized tables to select the values of the components of the filter, and then you scale it to 50 ohms with formulas. The other alternative is to use computer software, like, for example, ELSI, which is free. There's another one called SVC that's free as well. I've used ELSI a bit, but not the other. Looked at it, but haven't used it. So when you go through the manual design process, basically you look at what performance requirements you need, that being low pass or high pass or band pass or whatever. You pick, you pick the filter ripple requirements is if it's a Chebyshev filter, for example, or so you pick the maximum amount. If it's Butterworth, there isn't. You pick either the cutoff frequency, if it's a low pass filter or a high pass filter, or the bandwidth, depending on what you're doing. And then you go to tables and you get these normalized component values out of the tables, which are for 1 hertz bandwidth and a termination of 1 ohm on either side of the filter. Then what you do is you scale them with these formulas, and the formulas include the frequency and whatever load and source impedance you have. And the way you do this stuff is you start and you design yourself a low pass filter, and then you transform that filter into a bandpass filter that or a particular topology you want. For example, bandwidth, which is what I'm going to talk about. So here's a low pass filter. In the top, you can see it's got an inductor. It's got 2 load resistors. It's got a capacitor on the input, an inductor, and a capacitor on the output, and they're numbered 1, 2, 3. And the table at the bottom, this is a particular one. This is a 3rd order filter. And this is for the Butterworth filter. And you can see at the top, order 3, you can see the coefficients G1 is 1, G2 is 2, and G3 is 3 on that first line of the table. And the load resistance over on the extreme right-hand side is 1. So what you do is you take those values and you apply these scaling formulas at the top here. C1, for example, would be G1 times R0 divided by 2 pi times the frequency, and likewise similarly for the inductance. And you pick R0, most likely would be 50 ohms, and you use these GN values that I was telling you about earlier, 1, 2, and 1 for the 3 in order. And you pick your cutoff frequency, which for a low pass filter would be the 3 dB point, the minus 3 dB point. And you pick the bandwidth with you pick the bandwidth cutoff frequency to be 2 megahertz for a low pass, and that'll be your bandwidth. You pick that number to be the bandwidth of your bandpass filter you want. So then you get what comes out of that in this particular example for the 2 megahertz cutoff. It's a low pass filter. You get these values for the inductance and the capacitance. And you, the way it works, you normally these are the actual values you'd use, but what you do is you pick the closest value you can to get what you want. So that's how you get the low pass filter from these tables. And it works the same way for the other orders as well, and works the same way for Chebyshev filters and as Butterworth. So then, having done that, you want to get a bandpass filter. So what you do is you pick your bandwidth, and you use the bandwidth as a cutoff for the low pass design. So if you want a bandwidth of, let's say, 2 megahertz, you do a low pass filter with 2 megahertz as the upper frequency, the cutoff frequency. Then what you do is you pick your center frequency, whatever center frequency you want, and then you use it to calculate center frequency to calculate the various resonator component values, and I come to that. So you start with this low pass filter, same design here, same one I just showed you, and you add a resonator to each element of the low pass filter. So for each capacitor you put, in this particular case, you put an inductor in parallel with it on either side, but for both capacitors, and for the series element you put a capacitor in series with that inductor. Then what you do is you pick your center frequency, and that allows you to calculate, given you've already, for example, the through component on the bottom diagram on the top, you've already got the inductance from the low pass filter. You put in your center frequency, and it gives you, in the formula, it gives you the capacitance value you need. And so each filter is set up for you design it so that the frequency you use to design it is the center frequency of your filter. And when you're all done, you get a filter with in this case, with the 2 megahertz bandwidth and a center frequency of 2.828, like so. So here you can see the low pass filter response, and you can see the band pass filter resulting from those particular values, and you can see it goes through the well, you could see, yeah, it goes through the 3 dB point on both sides of the band pass. So that's the process you'd go through if you wanted to do it manually. Then there's this LC program. This is LC is a free program for, there's a student version that's free that gives you up to 7th order, I think it is. And basically with this program, what you do is you put in, you go through a process. You select the family you want in the second box on the below the top. You select the family you're looking for, and you select whether it's a capacitor input or bandpass or whatever on the right, and a bunch of other stuff. And basically what it does, then you click, I forget which one it is. I think it's analysis, and it does the analysis for you, draws a schematic, and then you get component values, and then you can edit them to be whatever you want. You can also edit the schematic. You can add, change the order, do this and that and the other. And the other thing you can do with the program is you can use the nearest 5% on the left side at the bottom of the 2 rows there, and that gets you more realistic values. It has a really good manual. It's a 132-page manual, and it's a PDF manual, so it's free for you to go have a look. So, a few years ago, this is going way back, for Field Day, we built some filters for the Mississauga Club, and they were all based on this left side design here with the toroids on the transformers on both sides and the 3 capacitors. And we built one for each of the bands we were using, and they seemed to work quite well. As far as we could tell, anyway. There's another one. So that was the N1AL filter. There's another filter. It's the with the more resonators. It's K4VX. So at one point, I did the design for LC for both of these. And here's the N1AL filter design with the ideal capacitor values, and you pick as close as you can. And here's the K4VX, similar idea. And when you're using LC, if you want to add another, see the numbers 1, 2, and 3, if you want to add another set of elements, you just go and tell it you want element 4, and it would put it on the right-hand side and redraw the schematic and everything. So having done that, you can then get it to plot several values on the same graph, and this is really handy so you can see what you got here. You can see the at the center, this is a 40-meter filter, so it's got virtually no loss at the top, 0 dB. I don't, what is it? It's it must be there someplace. I can't see it. Transmission loss 21 dB. No. At 40 meters, it's pretty good, virtually 0. At 14 megahertz, it's minus 21, and at 80 milliband, it's minus 25 at the bottom markers there. So as far as that's pretty good for what you want. And then this is for the N1AL, and then the other one is the K4VX, which you can see is much the same on the left-hand side, a little bit steeper on the right. So we did that, and I simulated that with LC, the design, and then I actually did a comparison using the mini VNA, and the curves are pretty much the same. As you can see, it gives you the transmission loss and the frequency as well. So that's what I know about using LC. There are other types of filters. There's the dual, I forget what it's called. Twin, it's a twin filter anyway, and it's got, this is similar to the design that we used for a double tune filter circuit. That's what it's called. This is pretty much the LBS bandpass filter design, except as inductance here, the design use transformers, similar idea anyway. And there's tables that you can use to come up with the various shapes and whatnot, and there's formulas to calculate the various components. This is from the ARL handbook. So I wanted just to finish off by talking a bit about crystal filters. So the quartz crystal on the left-hand side at the top, it's a piece of quartz, a thin wafer of quartz with two electrodes bonded to it, with the wires, the leads attached to that. And the way it works basically is depending on the thickness, it determines the frequency of the design. And if you excite the crystal, the atoms in the crystal will vibrate, and they will produce energy because they move. So you get energy going back and forth between the electrical energy coming in and the mechanical change to the crystal. When it goes back to its original state, it produces an electrical output. On the bottom left, there's you can characterize a quartz crystal. There's the symbol in the box. You can characterize a quartz crystal. It's nothing more than a tuned RLC circuit with what are known as the motional parameters, the inductance, capacitance, LMCN, and RM, the resistance, motional resistance. And there's a capacitor C0 that's accounts for the leads in parallel with the whole thing. And when you look at a crystal response, this is what, on the right-hand side, you get a peak followed by a very deep dip. And you certainly can't see that dip on a mini VNA when you look at it, I don't think, because it doesn't appear to have the range. And I'm not sure about the SNA. I haven't been able to find it with the PARC SNA either. So I've been fiddling around with the SNA, trying to learn how to use it. And what you do is you basically build yourself a little crystal test jig, which consists of a 3 dB pad on the left-hand side where the cable goes in, and likewise on the right-hand side. And then there's a couple of toroids that basically transform the impedance of it's a 50 ohm 3 dB pad, so you get 50 ohms out of it. The toroid transformers drop that 50 ohm to 12.5 ohms, which appears to be the standard value for looking at crystal analysis. As far as I can tell, there's an IEC standard apparently that talks about 12.5 ohms, and that's really hard to find. I found that in the video on Colpitt's oscillators, and I think I found it somewhere else as well. So anyway, what I did, the crystal I'm using is a 7.040 megahertz crystal, and when I was done, I got a resonant frequency of 7.037.6, so it's not quite 7.040, and I was somewhat surprised at that. But I guess that's why you have to put, that's why you have to put to pull them with capacitor, pull the crystal with a capacitor. Anyway, so and the C0, on the right hand side up above the plot, I got that from by measuring it with the my LC meter. That's how you go at measuring that. So this gives you the motional parameters of the crystal. And then what I did, I put it into, I haven't got around to actually building a Colpitt's oscillator, but I did simulate it on LT Spice. And you don't get quite the 7.037. It seems to depend on what particular capacitor lead, the C0 you use, and maybe there's other things going on as well. I've yet to actually put it into a circuit and try it out and see what I get. But at least the LT Spice simulation is reasonably good, I thought. And finally, this is, whoops. Where did it go? what's going on here? What's happened? Yeah, and finally, this is a crystal filter. It's got 4 crystals in series with capacitors between them and capacitors on the input and output side. And what this gives you when you put it into the circuit is an extremely sharp peak. And we discovered by playing around an LT Spice that if you have to put all the crystals in exactly the same rotational parameters. So we tried, Peter measured a whole bunch of, I think there were 4.9, and I simulated in the LT Spice and basically got garbage on the output. So it looks like they have to be virtually identical crystals to make it work, to get a flat minimal peak at the top with no dips in it. Anyway, so that's where I am. That's the end of the presentation. So yeah, any questions or whatever? Hopefully not, but anyway. Oh, good, no questions. That's good. So I'm going to stop the sharing.
Any questions? Any comments?
Well, I'm raising my hand.
Oh, I didn't see anything. Nothing
Can't
came up.
see it.
Okay. Okay, go ahead, Dave.
Well, let Peter go first. I think he put his hand up first.
Okay.
I say
Okay.
I know nothing, by the way.
I was just going to make a comment on the additional program. It took a while because I know that like Pete Giuliano had a lot of trouble with it. Matter of fact, I think he swore off it completely. And it took a little bit of time before I figured it out. But you reminded me of it, Michael, when you mentioned the crystals have to be all the same. And if you looked into that program, additional program, that's the assumption that all crystals are identical. Well, in the real world, we know they're not all identical. So it doesn't really work. So when I could see why he had those kinds of problems. So you have to really take into account that your crystals aren't going to be all identical. Because if you make the assumption that they are, then you're going to be disappointed in the results. A question I did have for you, Michael, was did you design a filter using the manual process and then compared it to the same thing with the computer simulation?
No, I haven't done that. I haven't done that, but I did at least go through the calculations to get the numbers that I showed in the slide. That I got the same numbers of the aerial handbook. Put it that way, but I actually haven't built one based on that. No.
Okay, thanks.
Mm-hmm.
Any more questions, comments? No, I guess not.
Oh,
very good, Michael.
Oh,
Dave,
good. I'm off.
Hey, Dave is putting his hand up, Ken.
Okay, Dave, go ahead. Go ahead, Dave.
Yeah, Michael, the problem with these filters is exactly what Peter said. All those software programs assumes the crystals are identical. And if the crystals are identical, you look at all the peaks, they'll all line up.
Mm-hmm.
But the minute you have different crystals, you'll get one peak, then another peak, then another peak. And so you end up getting ripple in the passband. So what you're seeing probably when you do LT Spice is you're seeing that ripple coming from the different peaks of each. Because if you look at that digital filter, each of those cavities with the crystal represents a harmonic, like a peak.
Mm-hmm.
And so you're getting the superposition of all these peaks. And so you end up with this ripple. And what you need to do, if you read EMRFD and you read that article that Wes wrote prior to, I can't remember if it was prior to EMRFD, there's a famous article he wrote. He specifically says, yeah, you use Dishel, you get your crystal, you build your filter, then you have to go and, you know those equations you use where you have G and N,
Yeah.
G of N and L of N and those kinds of things, you have to go use that now to go back and change the capacitor values, and you may even have to put an inductor in to get all the peaks to line up and you get no ripple.
Yeah, very, very involved process.
Yeah, and so
You
that's why I wrote that that Java program I've got, where you could go in and play around, because to calculate the actual values you need is very, very difficult. And I couldn't find any good reference that shows you how to calculate the values. It's very, very complex. So the program I wrote in Java, it's trial and error. It's you go through and you can quickly just go and try different capacitor values, and you could quickly see the impact. You could get the impedance either end of the crystal of the filter, or you could see what the ripple is, and you just tune it until you get the minimum amount of ripple in the passband.
Yeah. Yeah, I haven't actually done anything with that. Well, I think you sent me the program, but I haven't gone back to do any of that stuff. So
the other thing you could do, I bet you, if you sweep that crystal filter using the SNA, I bet you'll actually see the ripple in the passband that LT Spice predicts that you should have.
I should try that. Yeah. Okay. Anyway, that's what I had. So I'm going to stop the share and give it back to Peter. Or
Okay. We had another hand up. Fellow Gister. Go ahead.
It might be me, actually. I just joined.
Oh, okay.
So yeah, about the, it looks like the way it's been modeled, you've got the pure resistance there, sorry, the pure crystal there, and there's no resistance associated with it. So it's going to have a really sharp peak, and then that's why you would see those bumps. But a real crystal would have some finite resistance. If you model that in Spice, it's like it's called a Q spoiling resistor. It spreads out the sharpness of the peak of that resonance peak, and then it makes it kind of broad and flat. So then when you add them up, you'll see a much better waveform. Like your crystal filter will be a bit more realistic. It won't be as bumpy. It'll just be kind of there'll be broader peaks, and they'll add up a bit nicer. But you may have to just throw in a small resistance of some kind, even in Spice, just to get a more realistic idea of how the crystal filter operates.
Yeah, you'll see sometimes what they'll do sometimes is you can also get ringing in the passband if the Q is too sharp. So occasionally you'll see that they'll put some kind of resistance in the input and the output to lower that Q down a little bit.
Mm-hmm. Yeah, it makes it critically damped, so it reduces the. I mean, if it's underdamped, it will oscillate. It'll ring. Yeah, but adding a resistance will probably be an interesting thing to check out in Spice, because without it, it's completely synthetic. Like I don't even know what's limiting the sharpness of the peak. It should be infinite theoretically if there's no resistance. I guess it's the 50 ohms on the sides.
Exactly. If you change the impedance on the ends, you'll see the peak broaden out. And that's why, that's why I wrote that JavaScript, that Java program, is so that you could play around that and you could see the skirts change. And it's really interesting. It's a very, very complex. Crystal filters are extremely complex, and I think, Peter, that's why your comment about our buddy, Pete Giuliano. That's why he gives up on that, because it is very, very complicated.
I know when I did the LT Spice with the 4 or 6 crystals Peter gave me, Peter measured a whole bunch of them, and I used those, and it just wasn't right. Like it was all over the place at the peak, a bunch of peaks, like a bunch of ripple and stuff.
Yeah, the ripple.
Anybody else?
The Spice ripple may not be real, so it may not be something to worry about. Like,
Okay, Peter's got his hand up. Go ahead.
Yeah, I was just wondering on the number of orders. I know you talked very briefly about it, Michael, but is there a point of no point going any further, like 4, 5, 6, 7? Like I'm sure. What effect is it if you go too many orders? Is that where maybe the group delay comes into? I think you didn't really mention anything about the group delay, but what's the consequence of going too many elements or orders?
That I don't know. I know that probably from what I did see in the handbook, the higher the order, the sharper the drop off on either side. But I don't know if there's negative consequences either. I just don't know. Haven't looked at it. It's in the handbook. I'm not sure it really talks about that a lot in the handbook. It shows that diagram. It shows that diagram that I showed with the drop off, which would happen on both sides of the filter. But I don't know if there's negative consequences for that, other than the fact you got a whole bunch of more components now. So you've got to match them up or find the right values and whatnot. So it gets more complicated.
Okay, thanks.
All right, anybody else? Any more comments, questions? Okay, I guess we're going to move on here. So up the next two items is we education-wise. Anybody got anything to contribute towards that? I notice Eric hasn't got his Canadian license yet. Education. Nothing there. Okay, anybody working on anything they want to show and tell?
Well, aside from playing around with the SNA and trying to figure out how to do the motional parameters, I got a negative resistance at one point. It turned out I didn't have a ground on the crystal testing thing, and eventually I got that figured out. And I was using 5% resistors. Purportedly, there were 10 ohms. So when I did that, I measured the through impedance with the crystal place where you put the crystal bypass, and I got minus 6.29 dB with both the SNA and the mini VNA measuring it. And so Peter sent me some 9.1 ohm resistors that I put in as well, and that took the number closer to minus 5.98 or something. So it's a bit better, but the end result in terms of motional parameters was not all that much different. So I thought that was interesting.
Okay. Hassan had his hand up. Go ahead.
Yeah, so I got this display here for a Raspberry Pi. I was wondering, I wanted to hook it up to an Arduino or something similar. I was wondering if anyone knew how the interface worked, like how the pinouts and everything. Like, is it just a SPI bus? Because I think it's something similar to what we use in the SNA.
What make is it? Or what model? Is there a model number on it?
3.5-inch RPi display. There's no.
What's a display chip?
XPT 2046 touch controller.
No, there should be a chip. It's an ILI, or there's a bunch of different driver chips they have.
I'll have to see what that is. Yeah, okay. If I mail it to you, maybe you can help me out afterwards.
Yeah, take a picture of it. Find out what the driver chip is, because that's what the library you have to get that's going to match that.
Mm-hmm.
Is because that's the chip that's actually taking in the I squared C of the SPI, and it's putting that into whatever their raster or whatever technique they use for updating the LCD.
Okay, yeah, it looks like it's the XPT 2046. That's the only chip, and then there's these 4 other ICs, which I don't know what those are for.
Probably memory.
Could be like 74 somethings, 74 HC 49. So it looks like just something generic CMOS part.
Oh, high speed TTL.
Oh, okay. Level shifters or something.
Yeah, yeah. And 74 HC. That's high speed.
Okay, so it's so that's the touch controller is this XPT 2046. But
Where did you get it from?
I got it from eBay.
Oh, okay.
So just I couldn't find the specs or like the name of the part or anything, and it seems to be a Pi display, but I wasn't sure how to hook it up to an Arduino.
What does it say on the eBay description?
Yeah, they're also generic. It's really hard to find.
Oh, okay. Alrighty.
Yeah.
Anybody else? I just saw somebody put their hand up. Do it again. Okay, Peter, go ahead.
Nothing too much. The SIGGEN modifications is nothing new to report there yet. Hopefully something soon for next month's meeting. And other than that, I've been playing around a little bit with the 8307 chip again. Works fine measuring dBm. That no problem there. But I've been trying to convert that into watts, which I can get, but it's a little bit too coarse. So I have to mess around a little bit more just to see if I can get it to a little bit more accurate's not the word, a little bit more fine and a little more resolution, instead of going from say 100 watts down to then the next level's down 7 or 8 or 9 watts down and try to get it a little bit closer. Don't think I'll ever get it to go from like 100, 99, 98, 97, that kind of thing, but it'd be nicer to get it a little bit closer. I tried to cheat a little bit and look at Dave's SNA code to see if I could get some hints in there, but that was an exercise in futility. When I finally found where the area where I thought he was doing the math, I didn't understand what he was doing. But then again, I don't understand Dave half the time anyway. That's it from my end.
Okay. Hey, if anybody puts up their hand, do it several times in succession, because I'm not. Sometimes if you do it once, sometimes I don't get it. Go ahead, Dwayne.
Yeah, for Peter, what you might want to try doing is getting one of these little I2C 16-bit A to Ds, real slow frequency, but you don't need that, so you get much better resolution. And then use your attenuator, and you can basically go find out number of counts per dB, and then just convert that to watts directly.
Oh, okay, thanks, Dwayne. We'll look at that.
Okay, anybody else? Okay, good to go. No hands up. Alrighty. Oh, go ahead.
Are you in tiled mode, or are you just looking at one speaker at a time on the screen?
No, I'm tiled.
You're tiled? Okay, because when somebody puts their hands up, until they have spoken, there's a little blue indicator in the top left-hand corner of their tile that persists. So that's how you can tell, like, even if they only press it once, that little blue hand stays up until they unmute. So,
okay.
So there, Dave is like the king of, pressing his hand like a zillion times. But anyway.
You know what? That's okay for Dave doing that, because then I could see it.
Sure. I guess. I mean, it's keeping consistent with his personality. So I have one question about filters. Again, I just, most of that stuff was way over my head. But doesn't an ideal filter have very sharp drop-offs? Like, don't you want a filter to basically be a square wave? Or am I off on that?
Well, ideally that's right, but practically you can't do it with real stuff. That's the thing. That's why it's a gradual drop off. So ideally it would be exactly as you say, it'd be a square wave, but you can't do it practically.
So I'm thinking like the higher order. What I understand is, the more components you put in there, the sharper those those sides get, right? The steeper the drop off. So I mean, obviously there's some sort of balance between cost and complexity, but I would assume that you want to cram as many components in there, whatever they be, inductors, etc., to get those sides sharp.
I guess that's right. The other, I presume the more elements you have in it, the more likely there is to be ringing and those kinds of things going on too. I guess the ideal filters are the crystal filters because they're really sharp, very, very narrow.
Okay, thank you.
Can't hear you, Ken.
Hassan, you had your hand up?
Yeah. So Eric, there is something called the time bandwidth duality. So if you had just a boxcar filter, just it passes certain frequencies and it's zero everywhere else. It's finite in the frequency domain, which means it has to be infinite in the time domain. So it would take forever. It would just take, the delay through the filter would be infinite. You'd have to buffer samples from the beginning of time, and then go on until the end of time. And so that's the thing. The more orders your filter has, the longer the delay becomes as well. The steeper, the more finite it is in the frequency domain, the wider it has to be in the time domain. So there's always a trade-off there.
Okay, thank you.
Okay, Dwayne, go ahead.
Yeah, when you're choosing filters and it's more of an application-specific thing. If you know what frequency you're going to pass, what harmonics or filters frequencies you're trying to go eliminate, then you just pick the order of the filter that's going to be probably the most economical and easier to build and align, depending upon what you actually need in the overall circuit.
Okay. And Dave.
Yeah, if you look at an SDR filter, they're pretty much brick walls. They're very sharp coming down because the taps they have, like the typical filters we'll build are like an N of 4 or 5 taps, right? Whereas if you go to an an SDR filter, you've got like 50 or 100 taps, and you get a lot sharper drop off coming down. If you look at Charlie Morris's SDR radio he built, and you look at the filters he's using, you'll see he hard codes in the coefficients for the filter, and it's a huge list. Where's my diagram? There's my camera. It's a huge list of these coefficients he puts in to get a very sharp wall, sharp skirt. So Eric, yeah, you can get sharper skirts as you increase the N.
Okay. Well, I don't know if this is correct or not, but if you make the start and finish of the filter much sharper, so it's steeper, does it not ring more in the passband? Anybody?
I suspect it does, but I haven't really looked into that. I think that's probably right.
Okay.
Yeah, that's all stuff. Like that's why you got Chevy Chev and Butterworth and all these different types of filters, because they'll have different type of ringing characteristics. And I can't remember, is it elliptical filters?
Yes,
Yeah.
elliptical.
Elliptical's got the sharpest, right? But they've got ringing. They've got ringing at the what's it called? The cutoff band. The
3D point.
The stop band, yeah.
Yeah, there's a trade-off. So you can reduce the bandwidth, but then either the filter skirt becomes shallower, or there's more stop band ringing. So there's no way to get an ideal filter. You have to trade off something. And then again, you can get an ideal filter if you use a lot of coefficients or a high order, but then that comes with its own set of problems. And the noise goes up as well. Like even on a DSP, anytime you do a multiplication in a computer, there's a small bit of digital noise that's added to the signal, and it gets small. It accumulates over a while. So like nothing comes for free.
Yeah. Trade-offs.
It's called
Anybody?
it's called entropy.
As I said, there's no free lunch. I mean, yeah, you do one thing, there's a trade-off somewhere else. You pay for it somewhere else.
Okay, anybody else? Questions, comments? Okay, we're going to move on here. The next item was the roundtable on kit building practices. We're going to push that to the end. I think both Frank and I have got something to update on the direct conversion receiver project. I think the last video I sent out was with the analog VFO, which I didn't really like. I did hook up my SIGGEN, and you're gonna love this, Dave. It works beautifully, beautifully. The only thing that bugs me is the changing of the frequencies, having to go, between 100 hertz and a kilohertz and back and forth. Most of the time, whoever's doing the CW or voice, they're on a direct frequency, so you don't have to bounce around. But it works really, really well. That's going to be an option in the DCR buildathon kit whenever we do it. So, but go ahead, Peter.
Well, now that you've brought up the frequency selection there, maybe somebody somewhere along the way can design a direct key entry for the frequency selection.
Yeah, you could do that. Well, when I was using the SIGGEN, I would set it to a kilohertz, and then I would just go up and down the band. I wanted to check how well it worked on CW and the voice, and it works really, really well. And you can hear on the shortwave stations, you can really tune in that 0-beat carrier, so you can get all the voice. Occasionally, if I got a voice a sideband signal, I'd have to shift over to 100 hertz to tune the guy in properly. But other than that, it works really well. Basically, what happens is the VFO, the analog VFO is removed. A 40 dB attenuator is put on the line, and you plug in the SIGGEN and just dial in your frequency. That's it. It's really easy. So we're going to have that option in the DCR kit. And you guys can play around with that. Now, the other thing that I've been working on, and Frank also has been working on, is I still like the manual VFO thing. I didn't like the LC circuit very well. I found out that to control the voltage control was supposed to be 6 volts, and I invertedly hooked it up to the 12, and that would explain a lot of my drifting was going on. Best practice for transistors in an oscillator circuit is to try and keep the main voltage as low as possible. That way, it doesn't create noise on the base emitter junction, and it doesn't less current flows between the collector and emitter, and it prevents the from the die from heating up. So if it works well at 6 volts, then operate it at 6. If it works well at 4 volts, use 4 volts. The lower the voltage, the better it'll be stable. The other option we've been looking at was this a digital oscillator. I think it was the last mini had brought up that we had a long time ago. We got some sample kits, and one of the chips in the sample kit was the LTC 6900, and I'm going to share my screen here. Where is it? Here it is. I'm going to. Okay, can you guys see that?
No. Did you select application?
The application window. It won't let me share it.
First, you select share screen, then you go to the application window, and then select the application that you want to share.
That's what I got. And it's not allowing me to share. Ah, there we go. Can you see that?
Yep.
Okay. So this is the chip. This little packet kit comes with a different, about a dozen or so digital oscillators. They're all for different frequencies. Some are fixed. I think there's even one in there that goes up to a gig or something like that. But I'm looking at this one here. It's the LTC 6900. It's good for 1 kilohertz to 20 megahertz. Very, very small chip. Current draw is very low. We're talking about microamps. It's good up to something like 5 volts, and you can go down as low as 2.7 volts. But one note in their application is that when you get down to 4 volts, the frequency stability is weaker. So I've opted, and Frank's opted to stick to 5 volts. That's what it's optimally set up for. Output 100 ohm CMOS output driver, which I'm having problems with. Now, basically, it's like our analog VFO, where we're applying a voltage to a diode that's in parallel or series with the LC. And what I'm going to do is blow up the screen here. So you can see there on the right-hand side here is the basic formula. And the chip down in the lower left here. It's very easy to use. Your voltage, a shunt capacitor between the power and ground, and a resistor or variable resistor between 5 volts and the set point. Your output. Now, the way this chip in particular works, and a lot of the other chips, is you can divide the mass oscillator by 1, by 10, or by 100. So you can set what frequency range you want to work in. It is so small, I had to have 2 magnifying glasses to look at it to solder it onto an adapter board. And but I did get it going. So I have it going on the side of the DCR board. I hooked up, I put a 1K load on it, and I'm getting approximately 4.5 to 5 volts peak to peak on it, and very, very clean signal. What I tried to do is the same thing we did with the SIGGEN, is to put it through an attenuator to knock that signal down, and then go right to the pin 5 on the SA612. And for some darn reason, it just won't work. I've got signal on the input of the attenuator, but I don't have it on the output of the attenuator. And I do have a blocking capacitor in there, so it's not the DC. Frank has also been working. I don't know how far he's gone. I'm going to unshare my screen here. So Frank, you want to make any comments on your work on it?
Yes, I'll let everyone know what I've been doing. I want to just verify some of your findings, Ken, and I did try the DCR receiver using the PARC signal generator, and it worked perfectly, just as you found out yourself. So it's an excellent option, and one that will be included in the DC receiver. Then the reason for my going to something different for the variable frequency oscillator was because of drift. And it's not too bad if you let it settle down for about 20 minutes or so, but in the first 20 minutes, like any other simple oscillator, it is prone to drift. So in order to get around that, we both came up at the same time with the idea of using the 6900, and we both had one. It was delayed quite a bit because both of us had problems with this tiny chip and how to get it to handle practically. So I designed an adapter board. Ken found one commercially, but we put the chip on the adapter board, so we had a 8-pin dip connector that we could use in our experimentation. Now, we both wanted to set it up separately without using it in the direct conversion receiver, just to see how it worked. And when I put mine together, it didn't work at all. Ken was more successful, so I sent him the information that I was using, and it turned out that I had mine completely wired backwards. So, and the reason being is when I made up the adapter board, that I laid it out so it was on the back of the chip, back of the circuit, and then etched it. And of course, I put the chip on the front. So, or assumed it was a front. Anyway, I figured that that was it, that I let the smoke out, and that's the end of story. But then I wired mine up exactly as Ken had done, and lo and behold, it actually works. So this is some pretty hardy chip, I'll tell you. Not very often I let the smoke out and get it back in again. So then my concentration was on the input of this, whereas Ken was working on the output to connect it to the DCR receiver. Well, on the input, I was a bit more concerned as into how we can use the same components for tuning the DCR receiver, because it's a combination of 3 different resistors, basically, to have the input and the output, have the input such that you can have fine tuning as well as coarse tuning. In those experiments, I found out that the 6900 was very, very sensitive, or coarse, if you'd like to use that term. I measured the input voltage. It's a voltage control oscillator. And the input voltage at 7.0 megahertz was 3.826 volts. Then I moved to 7.3 and found it was 3.856 volts. Exactly 0.03 between one end of the band and the other end of the band. So that's why the tuning is so coarse on it. Now, my next experiments are that I'm working on now is to get a combination of control circuitry that will handle this and still provide fine tuning between 7.0 and 7.3. Now, whether or not we can get it stable enough to do that, I'm not sure. But that's where I am anyway. And back to you, Ken. Ken still there? Go ahead, Dave.
Okay, yeah, I've got a couple of comments. Let me just share my screen about the data sheet.
Yeah.
Yeah, go ahead.
There, can you guys see the data sheet?
Yeah.
Yep.
Okay.
Yeah.
So first thing here is, it says here, I don't know if that's the output impedance. It says it's 100 ohms CMOS output driver. So if you're driving a 50 ohm load, it means you're going to have half the voltage. It's a voltage divider, right? 100 ohms feeding 50 ohms. Isn't that going to be half the voltage coming out?
Yeah.
So right there, this is if that's the output impedance, you're going to have a voltage divider if you trying to drive 50 ohms. So you may need some kind of a buffer amp, or you need a transformer. The next thing I wanted to show you guys is frequency stability here. Frequency accuracy. You can see that it changes, the accuracy changes depending on the frequency you're at and the voltage you're at. Okay, and the next thing, and the charts, I'll show you some charts which support this, the rise time. So I'm not sure what this exactly means, but there's quite a variation in terms of the rise time, which is going to cause phase noise.
Yeah.
Because it's not rising the same each time. It's you can't see my arms, but I'm sure the rise and fall times is going to be quite different depending on the voltage and what's going on. So if you go down here now, you'll see the jitter. That's called jitter.
Yep.
And if you look at this chart, you'll see that here, depending on the voltage you apply. Now I don't know what these means, this numbers. I don't know if 0.8% PPP is really good or really bad, but I'm just showing you that the variation in jitter is it's frequency dependent. And that's what it was saying in the data sheet above, the frequency accuracy. So you could get, it seems as if it's pretty bang on around, what's that, 1, 2, 3, around 3 megahertz. As you get up to like 10 megahertz and beyond, you're getting quite a bit more jitter. Same thing if you go below 1 megahertz, you get quite a bit of jitter. Then if you go down, way down in the bowels of this document, where is it? Yeah, here. So here they talk about jitter, and they're talking about exactly what Frank, you were saying about power on. So here they're showing you that the frequency error, it's got to be powered on. Now this is microseconds, right? But you could see the frequency error changes how long it's powered on. But they're talking microseconds here, Frank. You were talking like minutes, right?
That's right.
Yeah, so you could see that there is some variation in frequency accuracy with time. So I would love to take that chip and put it on an SA, a spectrum analyzer, and just see. Let me turn off my screen here. Yeah, I would like to really put this on a spectrum analyzer to see the fundamental frequency and see if there are any spurs close to the fundamental frequencies, because that will be caused by phase noise. And if there are no, or the spurs are really low down, this is rock solid. But if you got some pretty big spurs, then you're going to be getting a lot of noise. So I'd really like to see how this performs on a spectrum analyzer, Peter.
Hey, Dave.
Wait, hang on. Ken, you live close to Dave. Why don't you drop off your board into his mailbox?
Yeah, I could.
Yeah, but my shack is taken up. What's that thing?
Oh, yeah.
This store again?
I've had enough. This is enough excuses. Get your shack together. Eric's going to get his shack together before you at this rate.
Is this an intervention?
We're all going to get together and sit 6 feet apart, and we're going to intervene with you, Dave. Yeah, hey, Dave, were you not with the HB group when we were on George Street?
Probably.
Yeah, I see.
When I joined was right when you guys did the Pixie.
The Pixie. Okay.
Oh, that was on George Street.
Yeah, that was at George Street. That was when I started coming down, was when you guys did the Pixie, and Gord was there all the time. I don't know whatever happened to Gord.
That's a long story. I know what it is. I'll explain it to you another time. No, in that case, everybody that was at that meeting would have gotten one of those sample cards from I forget his name. He was an Englishman. He worked for LTC.
John Barnes.
Yeah. Okay. He was also giving out a ton of SMD resistors, capacitors, transistors, regulators, and he was also handing out these sample cards. So
my sample card. I'll put a circuit together, but I haven't found it yet.
Okay. You might have one, Dave. You just forgot about it.
Yeah, actually, you know what? When I was looking at oscillators from my rockets, I got a whole bunch of these little oscillators here, and I probably have this guy sitting in a box somewhere. And you're right. The problem was all the because you get samples from Linear, right? If you write them, and so I got samples of a whole bunch of these oscillators, and I may even have this. The problem is, you're absolutely right. These things are just little tiny little things.
Yeah. Frank, would you happen to have the emails that had the photo of your board and the photo of my board?
I've got they're in here somewhere, but it would take me a little bit to find them, and longer even to find out how to share them.
Okay. When I built mine, I didn't have the exact adapter board for the chip, so I ended up using a TSOP adapter, and I actually got it to hook up properly, and I turned it into an 8-pin DIN package, or DIP package, and the board with the pin, without the pins, the board is 1/2 inch long and 3/8 of an inch wide. So that's how small it is. The chip probably takes up, I don't know, maybe 1/100th of that little board. That's how small it is. Like Peter does a lot of times, I just solder it right on there, and then I use solder wick to get the excess off. Because there's no point sitting there with a soldering iron and trying to make it perfect. But it's a pretty small package, very small. And on the side, when what I did, there's also something else in the data sheet too, is the maximum current draw is 50 milliamps, which works out to be the 100 ohm CMOS output. If you go any lower than 100 ohms, then you're going to be overdrawing on the chip, and it's not going to work. So what I ended up doing is, instead of using a 100 ohm load, I used a 1,000 ohm load, and it worked very well by itself. The only thing is, I got to try and figure out how to get it to work on the SA 612. And I've posted the question on the LTC forum, and 3 million people have looked at it, but nobody's replied.
Is it, Ken, did you say milliamps?
Did I say milliamps? I can't remember. Probably.
Yeah, because the data sheet is showing hundreds of microamps.
Okay, 50
50
microns.
It shows like 0.32 milliamps, which is 320 microamps.
Okay, I'm just looking at, see if I can find it again.
Yeah, it's on top of page 3.
That's with an infinite load resistor, Dave. If you have a good finite load, it'll be more. I think Ken was quoting with 50 ohms load, I think.
But is that little thing gonna really source 30 milliamps? Does it get hot?
I don't know. I'm looking for it.
Into a load, figure out what it is.
Okay, it says here on page 5. Output pin 5, oscillator output. This pin can drive up to 5 kiloohms and or 10 puffs load. Heavier loads may cause inaccuracies due to supply bouncing at higher frequencies. Coupled into voltage transients coupled into pin 5 above or below the supply will not cause latch up if the current in and out of the pin is limited to 50 milliamps.
Yeah. Holy shit, that's a lot of current.
Yeah. So so instead of going to 100 ohm as they specified, I went to a 1K, and it worked quite well by itself.
Could I ask a question of Frank?
Go ahead.
Go ahead.
Frank, did you say there was 0.03 volts difference between the bottom end of 40 and the top end of 40? Is that what you said to control the frequency of the chip? And if so, how are you going to do it? I mean, surely you want a wider range than that, right? Like, what are you going to do about it?
You're correct on both counts. Yes, it's 0.03 volts swing between the two. And the problem or the challenge now is how to fine tune a signal in the 40 meter band with that tight a parameter.
Yeah, we'd have to have some way of using a reasonable voltage and making it smaller somehow. I don't know how you do it. I have no idea.
Well, further experimentation was measuring the resistance I was using in both cases, and it actually turned out to be, in one case it was 28.13 K, and that's at the high end, and at the low end is 29.25 K. So actually you've got about 1K variation in there. So a 10-turn pot might do it, or 2 pots in series, one being maybe a lot less than the other one, and representing fine tuning in that case. There's a few tricks of the trade that I think I'm going to give a try to and see if I can control that. My concern is how stable is it going to be when we get down to CW signal.
Or you could use SI 5351.
Yeah, okay. Double the size of the kit.
We're trying to keep it simple.
Okay, go ahead, Peter.
Yeah, the problem that you were seeing, Frank, reminded me of when I was doing the experiments with the DCR, and I used the I did that reversed biased a regular diode instead of a varactor diode, and to see how that would work. And I don't remember the numbers now of the voltage swing to cover the 40 meter band, but I found exactly what you did. It was too coarse. You could hear the signals. It worked, but boy, try to tune in a sideband signal was a nightmare. In other words, it worked, but it wasn't good enough. So I'd be interested to see what you find if you can get this to work, because I didn't really pursue it any further. So hey, maybe a million turn pot might be the answer, Frank.
I'll order one.
Okay, go ahead, Hassan.
Yeah, just wanted to mention something. This chip is so small; it's ideal for something I wanted to build, which is a wireless temperature sensor. So I'll use a thermistor instead of the resistor, and just have a simple antenna with an LC circuit and a diode hooked up to VCC. So if I just pass in a carrier wave, it'll actually charge up the diode and the capacitor to like a voltage that'll feed into VCC, and I'll short the output. So then basically the square wave will just cause pulsations in the voltage line, and then I'll pick it up as backscatter from the antenna. So because this is a one chip tiny like solution, I can make it really small, basically just 2 or 3 external parts. And this is ideal for doing that.
Yeah, if you actually look at there's other application notes for this chip, and they actually give you temperature dependent circuitry to use on that.
Oh yeah. I built a prototype already using just a CMOS inverter and an RC, like R and a C, and it kind of worked, but it was a bit bulky, and I think this thing might be smaller and more compact.
I don't know if I have it still open here. There was an application,
a separate data sheet in the data sheet or something else.
Well, I think there was one in the data sheet, but there's also, they have separate application notes as well, showing how to use.
I see, temperature to frequency converter. They've got that here.
Yeah.
Where do you get these from, by the way? Like, what's a good place source?
The chip?
Yeah.
The closest one is DigiKey, and they're cheap. They're like $2 a piece. The only problem is you're gonna have to pay for shipping.
Yeah, $2 each. That's.
I think, if I recall correctly, it was $2. Oh, plus the cost of the adapter board.
Oh, you bought the a kit, like the eval kit?
Yeah, I've got. I had one of those sample cards from years ago that we all received, and I got it from there. It's got like 12 oscillators in it, different types.
Okay.
They are available from DigiKey, but look out for the lead times. I'm not too sure they're stocking them right now.
Yeah. They also have
samples. Couldn't you get samples from Linear?
Yep. You can ask for samples.
Okay.
Okay, go ahead, Cherry.
How much is the shipping, and like how long does it take these days to get the shipping from DigiKey? Like
from DigiKey?
Yeah, that's right.
Yeah, DigiKey's the next day.
Next day, and like I was wondering these days whether the shipping is delayed or something, and how much does it cost for these things like to get shipped? Like what is the shipping cost?
I think it's $8, isn't it, Frank?
Yes, it's a flat rate, $8, below $100. If you have a large order for $100, and the shipping is free to Canada. And I've placed orders as late as 5 in the afternoon local time, and I've had them here in my hand before noon the next day. So fantastic delivery, and if you have to pay for it, it's $8.
That's cool. Thanks.
The just so everybody knows, DigiKey's in Minnesota, but they also have a warehouse built at the Winnipeg airport. So when Canadian customers order, it doesn't come from Minnesota; it comes from the airport in Winnipeg, and that's how they get it out so quickly. I think who had their hand up? Michael, I think.
I'm just trying to. Just trying to figure out how to put my hand up. Do I just click on the hand and it comes up like that?
Yeah.
Or do I have to hold it down or what?
No, just click it and do it a few
Like that.
times. Yeah, do it a few times, and
So you're seeing it.
yeah, so I can see it. And
Okay. All right.
okay, you've clicked it, and you're on your screen. That little blue flag is not there, as Eric had pointed out before. Sometimes it does, sometimes it doesn't.
What little blue flag? Okay, that's fine. Okay,
Yeah.
I'll have to just click it. Okay, that's good.
Okay.
Thanks.
So that's where Frank and I are at with this right now. I'm like I said, I've posted a question on the LTC forums, and like I said, 3 billion people looked at it, but then nobody's replied. So I may have to take it a step further and start trashing the LTC guys on the forums. Anything else to add, Frank?
Not with regard to the 6900 or the DC, but before we finish, I do have one thing of interest that I have come across a SNA kit that has been completed, except for the labeling put on the case and also the SWR option. All of the parts are here. It was built by a very experienced builder. Let me see now. There it is there, sitting in the case, not finished. It's for sale at $50. So anyone who's interested in that, if they want to get a hold of me, I powered it up. It works fine, and it's available.
Okay. Alrighty. So anything else? Any comments, questions on the DCR? Okay, so our next agenda was the roundtable on kit building practices, but I see it's 9:10 already. Can we possibly push this to another meeting?
Sure, I don't have a problem with that.
Okay, and
No
I was
problem
hoping
here.
Okay, I was hoping that Klaus would be here because he would probably benefit the most. Some other people as well. And if we postpone it to another meeting, one of the off Wednesday ones, maybe Klaus can join in. Okie doke. Very good. Anybody else have anything to add? No hands? Okay, so I call this meeting adjourned.
Thank you, Ken. Nice job.
Yeah, thanks, guys.
Thanks very much.
Appreciate it.
Thanks.
Yeah.
Good night.
Next time.
Cheers. Thanks, Ken.
Yeah, take care. Eric, hang on a second.
Sure.
So, you and Dave going to do something for Field Day?
Yeah, I still have yet to do it. I guess I should, since we're only a week and a half away, but I'm going to invite at least anybody in the Homebrew group, post up there an invitation to come up here if they need space and they want to operate. So yeah, Dave at least said he'd come by and, whatever, just hack around, really. For me, it's going to be a lot of pulling stuff out of boxes that hasn't been used in some time. I've got an old Kenwood TS440 that I'm going to try and employ, put up an 80-meter horse fence antenna and let it rip. So anyway, that's my plan. I think Dave doesn't have anything to contribute because all of his stuff is already boxed up, as we were talking earlier. So anyway, and the offer still stands if you want to bring anything up and just have a spot to sit and operate. So.
Yeah, I think no, I haven't. I only have a QRP rig, and I don't. I'm not going to bother with that. I did talk to Joe 2 weeks ago. He said his offer still stands to use his equipment, but after I, as I told you before, I don't have room in the backyard for an antenna, a proper one, anyways. My own choice is to go vertical, and I'm not willing to spend any money to make one. It's not worth it. Now I am trying to keep my eye out for an R8, hopefully a used one, because they're going for like $500 or $600 right now, brand new at Radio World.
That's Cushcraft?
Yeah.
Yeah, right. Okay. I've got a Hustler. I forget the model, but it goes from 10 to 160, I think, if I'm not mistaken. But it's a vertical that, again, has never been taken out of the box. But, I might throw that up just for the hell of it, put it on the side of the barn or something like that, figure out how I can attach it. I mean, I've got that 40 foot field antenna, the one that pushes up that I've brought to field day, the portable. So, whatever, some combination, just hook something up and, just see what happens. But yeah, we're not doing any submissions as a club though, right? Is that correct?
No, what you do is you operate on your own.
Yeah.
But when you submit your log, you can also submit the club's call on it. And then everybody who submits the club call on their logs gets contributed to PARC.
Oh, okay. All right. So there is some attribution still as a group. Yeah. Okay.
Yeah.
I didn't see that in email. Yeah.
Yeah. If you don't put the PARC call on it or the PARC club name on it, then it won't go towards the club.
Oh, okay. All right. Because it sounded very individualistic from Richard's email that I saw, but
yeah, it's kind of cryptic. He didn't explain it very well, but because I had that couple of Jitsi meetings with them, I knew exactly what he was getting at. So if you log anything and you go to send it in, make sure you put the PARC club name on there. And everybody who operates can put it on there too.
Yeah, I'll make sure I let Richard know as well that I'll be doing that. I think he wanted to have some sort of advance notice of who's on what bands and whatever. I guess.
Yeah. Now I would not mention that you're inviting anybody up to your place because they were very concerned. They want everybody to work on their own from their own house. They don't want anybody getting together. So you're probably better off. Not inviting.
Even just in a homebrew group, you don't think? No.
No. Like I might be interested to come up for a few hours and just see what you're up to. I think you said Dave was going to come up.
Yep. And Peter kind of hinted he might come, but I don't know. No concrete discussion. So, all right, well, I'll keep it just within the an email, I guess, between the interested parties. So. Yeah,
just keep it to yourself, and us, Dave, whoever else.
So they were pretty clear on the communication about that, though, eh?
Yeah. They want the social distancing to stay intact.
Yeah. I mean, because I was gonna, say, hey, this is totally unendorsed. This is just a personal invitation, but still, I guess, I don't want to rub anybody the wrong way. So.
Yeah. Okay.
All right.
Yeah. So once you email me a map where you live, and we'll keep in contact. Maybe I'll come up there for a couple hours.
Yeah. Sure. Absolutely. It'd be great. All right, Ken.
Okay. All right.
Thanks again.
Yeah. Take care.
All right. You too. Have a good night.
Night.